All right, so welcome back. We finished out arrays last time. So this is kind of a one-off lecture that corresponds to Module 8 or Module 9. Remember that they're flipped because of the a modified 14-week schedule. Next week is your midterm. Monday we have a review session, and Wednesday we have your actual midterm. So during the midterm is usually when I cover debugging and tooling. Because it doesn't necessarily require, it's necessary for necessary skills for you, but it's not something that's going to be required for the midterm, explicitly at least. So remember that we are on Piazza for live Q&A. And I'm going to be going over a whole bunch of tools here, and I just want to draw your attention to the fact that a lot of these things are in one of the documents available on GitHub that I'll bring up later on troubleshooting. Some of the stuff you've already seen before. So for example, under tooling, I mean, you software developers, software engineers, whatever you want to call yourselves, you use a lot of tools, right? It's not just code, right? A lot of stuff that you've been doing so far is just code, but implicitly you've been using a lot of tools because nobody codes in the dark. Nobody codes by themselves. Instead, you need to collaborate with a team. You use libraries. You have dependencies. Complex projects, other than a Hello World project, start requiring much more powerful and complex tools to start dealing with the complexities of those projects. So what I want to do is I want to bring your attention to some of the tools that you've already used. For example, this is not live updating. Just a second. Let me go ahead and close this and restart it. Mark down. 1 second, sorry. Otherwise, I would have to save every single time. Must have lost its connection somehow. All right. There we go. So tooling. One of the tools that you used from day one, or at least we exposed you to this, is source control and software versioning. What tool have we introduced you to take care of that? Git, right? GitHub is, it's important to understand that GitHub is just a company that offers, web-based Git repositories. Git is actually free. It was created by Linus Torvalds, the same person that created Linux, and for which Linux has its name. You can use Git if Git is free. GitHub is, well, now it's owned by Microsoft, but it is a company, a for-profit company. Git is completely free and open source, right? It is a great tool for keeping track of your software, for managing your software and keeping versions of your software. GitHub also adds things on like bug tracking, bug reporting, forking of projects, publicly available projects on GitHub, etc. There are plenty of competitors to GitHub, by the way. GitHub is just the biggest because it's the most well-known. One of the direct competitors is Bitbucket. And until Microsoft bought them, Bitbucket was a better alternative as far as pricing went because they did give you free private repos. Now GitHub does that. They changed their source of revenue more for the enterprise kind of level stuff where they get large organizations to pay them tens of thousands of dollars instead. And of course you have free alternatives like GitLab. If you're a student, of course, you have access to git.unl.edu as an alternative if you want to use that. And that's an instance of GitLab. So of course you've got Git. You've also got old and broken, not broken, but old and grimy, I guess. Competitors. That GitHub, I think, is about 15 years old now. I forget. It just had its 10th anniversary a couple of years ago. Maybe it's between 10 and 15 years old. I forget how old it is. But before that, we had like really bad one called CVS, Content Versioning System. I think it was, CVS or SVN. SVN, Subversioning System is what it stood for. Those are older ways. These tools have all existed for a long time. It's just that Git is a distributed version control system. What that means is that the entire history can exist on multiple computers at the same time. CVS and SVN, they were centralized content versioning systems because they kept everything on one server. You would have, on your computer, you would have a copy of the current repository. You could branch off and make changes to it and then push that up to the server, but otherwise everything was kept on one server. With a distributed version control system, that means that everybody's got their own copy, everybody's got their, can work completely independent of each other, commit their own stuff, and never have to push it back to a central repository. It seems kind of antithetical that GitHub is now ruling the Git space, because it takes it right back to the centralized authority of one server ruling everybody. But it's a little bit of a contradiction, but Git is intended to be a distributed version control system. Hopefully you've navigated at least the basics of it, and really all you need is the basics of it. But hopefully you've navigated enough that you are actually using it for your own code going forward. If not, then you need to be doing that. And there are plenty of tutorials out there. OS2G, a student group, just held a seminar last Friday that I tried to advertise as much as possible. So you can learn this stuff from online, or there have been plenty of opportunities. I think that there's been a seminar like that every semester for the last couple of years. So if you want to learn more about Git and you just want to get more into using it, advanced stuff, make sure that you're taking advantage of that kind of stuff. Another tool that you have a passing familiarity with. Each one of these tools takes a long time to master, by the way, which is not the focus of this course. So I just try to bring them in on the edges, on the periphery, so you get exposure to some of them. Not necessarily that you'll learn them hardcore. The other one, of course, is build systems. Right? The build systems that I've exposed you to so far are Make, or the more modern CMake. We haven't used that one directly. But build systems are important because once you get up to a certain level of complexity, you can no longer just go gcc foo.c and run an a.out file, right? That's basically for just very simple hello world kind of stuff. Even if you only have, say, a dozen files, like you had in Lab 6. You have things in like image utilities, color utilities. Then you've got this STB image over here, which actually handles the persistence out to like a PNG file or a JPEG file. That's where all this stuff is done. I never wrote that. I just stole that from somebody else. It was free and open source, so you're not stealing, technically, especially as long as you retain their copyright notice at the top, which I did. Yep, there's the copyright notice at the top. Public domain, so he put it in the public domain. And we've got a bunch of other files here, etc. How do we bring all these together? We bring it through a make file. And now this, even by the standards of a build system, this is still extremely simple, right? You can get much more complex than this. You can get into conditional builds. For example, oh, I want to build this for Windows. Okay, well, then I'll branch off and does this thing exist? Yes or no? Okay, well, no, then go ahead and go to this thing. If this thing doesn't exist, then fail, or you can have really, really complex rules. These are just simple rules that I built. You do have variables, just like any programming language. CC here is for the compiler. And the compiler here that we're using is GCC. Of course, you can change that around. There are lots of other compilers. CLang is another compiler that you can use. Here I'm compiling it with the GNU 99 standard. These are flags that I put in. I make sure that all of the warnings are turned on. I make sure that the math library is in there. And I put those variables in all the build statements here, because if I ever want to change this and, oh, I don't want the math library, or I want to include another library up here, then all I have to do is change it at one variable, just like you do in a C program, right? But the rules here are basically, it provides this is the thing that you want to build. This is the artifact that you want to build, these are the dependencies. These are the files that it depends on. So if you want to build the image driver here, then it depends on this imageutils.o file, object file. It depends on this object file, colorutils.o, and it depends on this imagedriver.c file. Well, transitively, how do we build those? Because we need to build these three things in order for it to work. So make, the utility, will go out and see, okay, well, that file exists, we're good to go. Oh, that file does not exist yet. Okay, well, how do I build it? There's another rule. How do I build this .o file? It depends on these files. So we've got a transitive dependency that, okay, now this file has to exist and this file has to exist. And how do we build it? Well, we build it with gcc std GNU 99, provide any of those flags, so turn on all the warnings, put any of those includes that we have, and then we compile images.c into an output file called images.o, imageutils.o. And that's how we end up building it. So that with one command, make, you can make an entire utility. Now imagine if this were hundreds of source files, right? No way are you going to be typing that out every single time. Instead, you create a make file with the transitive dependencies and how do I build everything. And also you have other utilities like this, clean. I want to clean up all those object files and all those development files because I'm done building it. Well, it'll go ahead and remove all those files for you, according to the rule that you put here. Right? If, in case you're wondering, these are tabs that is required by the make file language. But otherwise, this is a pretty simple example of a make file. How do you build color utils tester.cmaka? Well, it's this thing, but also you need to link in the cmaka library, right? So there are lots of different things that you can do with make, that's just the tip of the iceberg. In a real build system, you also have dependency management of external libraries, right? And the example that I'll pull off my head right now is in Java, you use a build system called Maven. In Maven, it's actually XML based, so you can define all your rules in XML. And then you can go out, Maven will not only build, with Maven, not only do you know how, can you specify how something is built, but also, oh, by the way, I rely on this library, external library like cmaka. Go out and download the latest version for me so that I don't have to maintain it locally. Right? And oh, by the way, that library depends on those 3 other libraries over there. It'll take care of it automatically for you. Right? That third library that it was transitively dependent on also depends on that, and that, so it'll bring all those things in. Package management is basically what that is called. Package management. Right? Also, all of this stuff falls under a heading called DevOps, right? Development operations, right? I think I've mentioned it before, but you know, this can writing make files, writing build scripts, writing Maven scripts. That can be an entire position, right? They call themselves DevOps. And of course, you can write scripts to push the build out to production, or push the build out to the download site so that your customers can download it, or push it out to 50 different machines automatically. All those scripts are, somebody had to write and maintain all those scripts. That could be a multiple full-time positions when you really get down to it. And it all falls under the heading of DevOps, right? Which is, again, why we only expose you to the periphery of these tools, because that could be a full-time job, a $150K a year job or something if you're out in California, right? Definitely not in Nebraska though, right? You've also been exposed to unit testing, right? And that's actually only one small amount of software testing. There's also, you know, regression testing. There's load testing. There's fuzzing. There's a whole. I could not off the top of my head, but you could list a dozen different ways of testing software. Integration testing, et cetera, right? I only exposed you to unit testing. I did it in a couple of stages. We did it through ad hoc testing, where you just simply run your program, right, and manually test it. Okay, yeah, I input 10, and it divided by 2, and it output 5. Oh, great, it works, right? Then I showed you more informal, right? That was repeatable, that you actually wrote code to test your other code, right? So that it's an all automated process, so that you can rerun it. So that if you make changes to your software, you can go back and test those for regressions. Things that were working before, but now because of your changes, they're no longer working. It needs to be repeatable. And then, of course, a formal framework like cmaka. Right? cmaka is only one of dozens out there for C. Right? For other programming languages, there are some de facto ones, like in Java, it's JUnit is the de facto unit testing framework, but there are several others that you can choose from. Basically, it relieves you of the need of doing all that boilerplate stuff of run this test and add it to this test suite and make sure that, and then give me a summary at the end, right? Instead, you just write the minimal amount of code and use a testing framework like CMOC or JUnit or something, okay? I've also exposed you to at least a few static analysis tools, right? So remember what static analysis is? Static analysis is an analysis of your code before it compiles, right? Statically, right? For example, GCC can be used as a linter, right? Do you remember how to do that? And then making sure that you're always using what flag? The WAL flag, right? In fact, just before I came here today, I was in office hours and somebody came in and asked a question that it's been crashing or whatever. They shared their screen and I looked at their code. I immediately saw it, but that's because I've been doing this stuff for a long time and I know what the common mistakes are. And so instead of telling him right away what the error was, I said, are you building with WAL? Nope. Okay, let's do that. Built it with WAL and it immediately came up as a warning. I go, now do you see the error? So we looked at the error, and he was using an equal sign instead of equals equals. It was perfectly fine to go ahead and to compile that and see. And if you didn't compile it with the WAL flag, GCC was happy to do that for you, right? And of course, it was segfaulting out because he was making it equal to null, which lost the reference, which later on meant that when you dereference it, you get a segmentation fault because you are dereferencing a null pointer. Remember Bret Hart hitting you over the head, okay? You've seen that video, right? All right, it's in the required viewing. If not, Bret Hart null pointer dereference. There we go. You're not going to be able to hear it because I'm broadcasting, but he's yelling at the programmer here from the 90s that he's dereferenced a null pointer, and Bret Hart doesn't hit him. His colleague hits him over the head for doing that. That was from some promotional video from the 90s for some wrestling game that was being developed. So always remember that, though. All right? Anytime you're dereferencing a null pointer, just remember Bret Hart and let him hit you over the head for dereferencing that null pointer. But anyway, you can use this as a linter. Another one that you might want to start using, another flag, is going to be for GCC is wextra. Right? So some things will show up under wextra that will not show up under WAL. It's counterintuitive, I know, and it's stupid, I know. If you said all, give me all the warnings, you meant give me all the warnings. Well, it turns out that's not all the warnings. There are some extra warnings out there. Right? Here's an example. This is not the same example that we used when we looked at linters before, but here's an array program. We'll take a look at the internals of this in a second. If I don't list any warnings at all, it's a perfect build. It's a perfect compile. If I start listing all of them, oops, there we go. Then I get 1, 2, 3, 4 warnings, I think. 1, 2, 3, 4, 5 warnings, right? But if I add WAL and wextra, I get even more. I think, well, it might be the same. Okay. It might have been the same, but you can certainly get extra ones later on, right? For this particular example, it didn't work out. But you can go ahead and use that as well to get even more warnings out of GCC. Clang is another compiler that we haven't used much, but it is installed on the CS50 server. And you can use it as a full, what's called a static analyzer, which is what we're talking about here. You can go clang, or not analyze, there we go, foo.c. And that'll analyze your code and give you many of the same warnings that GCC does, but it does have maybe some extra that don't always show up. For example, let's go ahead and go with Clang, and it's also on the CSE server. Analyze this array program that is buggy, right? And I get 3 warnings. For example, potential leak of memory pointed to by array, right? I didn't get that warning from GCC. I got that warning from Clang. So using a variety of tools here, I really wish there was one tool that ruled them all, but there's not. In fact, there are tools out there that companies pay $50,000 consulting fees for this other company to run their highly specialized static analysis tool on their software to find out whether or not there's a bug, right? So there's money to be made out there in these tools. These are just the open source tools. So if you're going to complain that there needs to be more, then great, go ahead and join that open source group and start contributing to it, right? At some point. You also have another one from Facebook. I don't think that this is on CS50, but I had them install it on the CSE server. It's a tool called Infer, Facebook's Infer, right? Which is a static analysis tool. And you can use it like Infer Capture. And then this is not, there is a space there, GCC foo.c. And then later on, you can analyze it. Infer, analyze. There we go. So let me show you that as a demonstration here on the same program, array program. Right? And what it'll do is it'll run through and run an analysis on it. And there's the output there. To actually analyze that, you would go infer, analyze, right? Wow. There we go. What do you see here? It was able to detect a memory leak. Awesome. Just like Valgrind yesterday. But Valgrind was not a static analysis tool. Valgrind is a dynamic analysis tool because you actually had to run the program, right? Static analysis tools can predict bad behavior before you even compile. There's a null dereference. So Bret Hart here is part of the Infer tool. Null dereference, memory leak, dead store, right? This is never actually used. You only ever set it, right? Uninitialized value. Wow, that would have been helpful for a lot of people yesterday in their labs that got NaN as a result. Why? Because we never set the total if we're going to be adding stuff up. So lots of tools that would be very, very helpful as you go forward into more and more complex programs. And then, of course, you have dynamic analyzers, dynamic analysis tools. Right? Dynamic is basically kind of the same thing, except that it runs the program. Right? Dynamic analysis occurs when you actually run the program. Right? So, for example, Valgrind from yesterday. And I'm just going to cut and paste this because, there we go. You ran it like this yesterday to check for all memory leaks of all kinds and show me all the kinds of memory leaks. But its utility doesn't just end there. Let me go ahead and cut and paste this, and I'll show you what I mean. But first of all, I'm going to have to compile this with a special flag that we're going to come back to here in a second, -G. That kind of counterintuitively stands for debugging. It's because of GNU's debugger. So the G flag, GNU Debugger, GDB starts with G, so they use the G flag on it. And then array program. You have to do. You don't have to do this, but you have to do this in order to preserve line numbers. And I'll show you what I mean by that here in a second when we actually run this. Oops. A.out. is what I compiled it into, and then Valgrind, not Algrind. Oops, what did it do? It's right there. Oh, I know. /, sorry. There we go. All right, there we go. Segmentation fault. For why? For what reason? Well, there's no memory leak in this yet, but of course you observed a memory leak yesterday. What did it do? Let's see, where is it? Invalid write of size 4. 4 bytes were written to a memory space that was illegally written to, that didn't belong to me. Where did that occur? On line 26. If I had not compiled with the -G flag, this line 26 here would not be preserved. It would be just say, somewhere in the program, in the actual machine code on this machine, at this byte is where it occurred. And that's not going to be helpful at all to you because you don't know where the hell that is in the compiled program. So on line 26, something is happening. Address 07 is not stacked, malloc, or recently freed. So something's happening on line 26 that we're going to detect later on. But you can use Valgrind to detect out of bounds, right? If you try to access, say, I'll show you that array program.c. Let me go ahead and do both of these. So GCC, all right, and run valgrind again. Wasted some space. I'm intentionally wasting space just like in your lab yesterday. But also I'm doing some weird stuff. There we go. So lots of bad things are happening up here on lines 62, on lines 58, on line 64. For example, invalid write of size 4 at line 62 occurred, having been called from line 22 originally. 4 bytes before a block of 400 was allocated. 400 bytes were allocated, right? And we were able to write within that 400 bytes, but somehow we wrote before or after that, right? In fact, it says 4 bytes before a block. I wonder what happens there. Let's check out line 62. Line 58, something similar happens. Or here, line 64, something similar happens, but it's after the block. Let's see what happens on those lines. So help me out. What was it, 58? Lines 58 and 62? What happens on line 58? So that's where it was allocated. It said 400 bytes was allocated. What does that correspond to? 100 integers. Each integer is 4 bytes. That's what that third question was asking you in your lab yesterday. It said 40 million bytes were wasted or leaked. What does that correspond to? Well, 10 arrays of 1 million each, 10 million integers times 4 bytes each. That's 40 million bytes. That's what we were getting at there. So what happens on line 60? Well, nothing happened on line 60, I don't think. What happened on line 62? What is I? -1, before the memory stack. What happens on line 64? I is now 100, 4 bytes after the memory stack. And valgrind can detect that because it's keeping a very close watch on everything. That comes at a price, of course, because it is actually simulating your program instead of actually running your program. But if you're trying to debug it, then of course you don't care that it's going to take longer to run because you're not in production yet. You're not running it as intended. You're running it to debug it, right? All right, good. Actually, let's go ahead and get rid of those two. We don't need to show the memory leak either because that's exactly what happened yesterday, right? I just simulated it again. And so we create 1 million integers. We make sure that the compiler doesn't compile away and optimize it by using the first one and the last one. And then I set it equal to null. I intentionally leak it, right? And I can't free it up at all. And so I say I wasted some space, and then I pause for 1 minute so that the program doesn't just, immediately stop, right? All right, save that. Recompile it, and ignore the warnings for now. We'll get to that in a second, okay? So valgrind can be used for a lot of other stuff than what you just witnessed in lab 7. You also have perf testing, which I'm not going to go over today, but we will revisit this when we start looking at searching and sorting. It's basically, perf testing is short for performance testing. How efficient is a program? It might be correct. It's completely bug-free, but it's also really slow for some reason. Why is it slow? Where is it spending most of its time? Oh, it's spending most of its time in that function. That's where you should focus to see, can I rewrite that function to be more efficient? And to do that, there's a tool called a profiler that will run the program and tell you how many seconds it spends in a particular line or in a particular function so that you can focus your optimization efforts there and see what's going on, right? And for the one that we'll look at later is called gprof. It's GNU's profiler. So again, why think of a clever name, right? People try to think of clever names all the time. Like Python people especially will do that. They'll try to think of anything Python or snake related to call their stuff, or Python like a or stick pi in front of something to make a pun of some sort. The GNU folks, they're not so concerned about puns, and so they just call things what they are. All right, but the big tool that I want to give to you today is a debugger, a proper debugger, right? And for that, I saw this hit the top of Reddit today. line 31 was not a bug. 14 bugs remain. I thought everybody played Among Us. The one guy that usually plays it is not here today. All right, so be it. All right, so anyway, they casted him out. They voted him out of the spaceship because they thought he was a bug. It was not a bug, and in fact, they still have to find the bug. All right. So the poor man's debugger, are what you may have been doing up to this point, printf statements. What value does this variable have at this point in the program? Print it out and find out. Okay, well, that looks all right. Go ahead and delete that line. Make another line somewhere else. Or make 50 different printf statements and then print them all out and then go back and delete them all. Ah, crap, I've got another bug. Put them all back in, all right? Yeah, and this is a never-ending cycle of poor man's debugging, right? That you're wasting time. You're just spinning your wheels by doing that. Instead, you'll want to use a proper debugger. And for C, that means using GDB. Now in the CS50 IDE, they have this little debugger over there. I still haven't figured out quite how to use it. If anybody does, go ahead and please let me know and show me. But otherwise, I think it's just a thin wrapper to GDB. I just haven't figured out the graphical user interface yet. But GDB is on the command line. It's basically a command line debugger. It's available on both the CS50 IDE and the CSE server. And it's GDB. It stands for GNU's Debugger, right? A debugger, what is a debugger? Well, it doesn't actually debug anything. It just allows you to debug stuff. You're still the user. You're still the debugger. So a debugger is actually you, but a debugging program is a program that simulates, runs another program, and allows you to pause the execution. Because of course, every program is kind of ephemeral. It's as long as it's working, it's going to be done in a matter of milliseconds, right? And that, of course, is not conducive to a human saying, what's going on here? Because it's already done before you can even say the first syllable of that sentence. You can view variable values, right? You can step through a program, line by line, right? You can set breakpoints to pause the execution at a particular function, line, or under some condition, right? Pretty cool. It's very, very powerful. It actually even lets you step through a line by line of the actual, well, source code, of course, that's what you would want to do, but you can also actually go to the machine code and to the assembly code and walk through line by line of the actual assembly if you really need to. And so it's very, very powerful. And GDB is GNU's Debugger, right? It just stands for GNU Debugger, right? Is a command line or TUI, text user interface debugger, right? So here's how you use it. Always compile with the G flag. It preserves variable and function names as well as line numbers. If you do not preserve line numbers and stuff like that, it can only ever show you the machine code. Because when you compile a program, it compiles into machine code, a bunch of zeros and ones. You don't even have the assembly, and so you're just blind. It'll say, well, it's seg-faulted, and here's some information about it, but you'll never be able to map that back to the original source code. The G flag preserves all that metadata inside your program. You don't want to use the G flag for an actual final build because it would be much larger than the original. For example, let's take a look here. If I just go ahead and GCC array program, and I look at the size of a.out, then it's 12K, 12.5K. But if I use g.a.out, oops, GCC, not a.out, but there we go, and look at it, now it's only slightly bigger in this case, but of course you can imagine if it was a much more substantial program, then it could be double or triple the size. I don't know that it affects the runtime of it, since it would just be metadata within it. It's probably just all located at one segment of the program anyway, but it's not something that you want to do for the final version of your program. But you do want to use it if you're going to debug, because otherwise you won't know what line number you're on that it failed. Now, to run GDB, use GDB a.out, where a.out is your compiled executable. So if you compiled your executable into image driver or into test driver or utils tester or something like that, then of course you would replace a.out with that. Let me show you what that looks like now. Let me go ahead and make sure that I do it once more. There we go. GDB array, or not array program, but a.out. That starts up GDB, and you know it's a command line thing. It's a text user interface kind of thing. And so that's not, I can run the program, of course, and it immediately segfaults out and takes me to the line at which that happened, right? That's not all that useful. So what I'm going to do is I want to look at all my, I don't want to look at just that one line. I want to look at it all, right? So I'm going to go ahead and go with layout next. Right? That allows me to look at the program, and I can even hit the up and down arrow to look through the program. I can also go to layout next. You're not going to want to do this in practice, but I do want to show you. Ooh, cool. There's the assembly code. Layout next. There's the assembly code right next to the original source code. There's the machine code, the machine code, raw machine code there. Layout next. Layout next. Right. There we go. Now we're back to the original. Right, where I'm just looking at the source code. That's where you're going to want to be. All right. So, what did I just run? To run your program, you can go with run. Simple enough. To view your source code, you can use layout next. Now, if I did that first, of course, there's nothing running. So let me go ahead and exit out of this, or quit. Sorry. All right. So how do you quit? Quit. All right. GDB a.out. If I went immediately with layout next, of course it's not going to show me anything because nothing is running. I now have to run something in order for it to show me something. Sometimes it screws up like this. That's okay. You can hit refresh, and it'll redraw the screen. Right? So sometimes it screws up. Just type refresh. Right? Once you've done refresh, then of course you can go back and check it out. Right? It stopped here automatically. Why? Because we got a segmentation fault. At that point, you're kind of dead in the water. I want to know what happened before that. Right? So what I want to do is I want to set a breakpoint. I'm going to start way at the beginning. So I'm going to start at main. You can set a breakpoint, break at main. That sets a breakpoint, and you can see this B+ right here. Or alternatively, you can set a line number in a particular file. So I could say break at line number 19. Right? You see that added another breakpoint over there. Right? Making sure that this is visible. You know what? Sorry. My head is covering some of this, so I'm going to go ahead and, there we go. That's better. All right. Refresh that. There we go. So I've set these breakpoints here. Now it's already running and it's already down here below, right? Remember that it stopped at line 26. You can always rerun the program from the beginning. Run, and yes, restart from the beginning. Refresh, and you see that it stopped there. In fact, it went into a capital B. It stopped. It didn't stop because there's a segmentation fault. It stopped because I told it to stop there. Right? Now I want to go through line by line to see what happens next. So I can type next. That'll go to the next line. Next, right? It prints out garbage, so there's a bug there of some sort. Next, right? And again, refresh every so often. My finger is going to get tired doing next every single time, so you can just go next, 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 right? Of course, the program no longer exists. N. So you can set breakpoints. you can set a function breakpoint. For example, break main, or whatever your function is called. You can set a line breakpoint. Break, and then the line number, say 12 or something, right? Of the current file, or you can provide another file name, then a colon, and let me write it down. You can set a line break point in another file. So break file.c line number 26, right? So if you've got multiple files that you've all compiled together, like say a utils or utils tester, you can set a breakpoint in the other file and then run to that, right? Well, let me rerun this from the beginning. There we go. Refresh. All right, well, I don't care about that breakpoint anymore, so let's go ahead and unset it. I think it's clear 15. Yep, there we go. Nope. Clear main is what it was called. Okay, refresh. There we go. Now the breakpoint is gone. Because I fixed that bug. We haven't fixed that bug yet, but of course, you can also clear breakpoints. If you quit out of the program and come back into it, of course, that's another way that you can clear all your breakpoints. But that's not something you want to do live, right? You can clear a breakpoint by using clear main or clear. What did we do? 12, right? We set a breakpoint at line 12. We can clear 12, right? But our program is still paused. Now, if this for loop ran for 100 iterations, I don't want to hit next 100 times. So what I can do is I can say continue the program until the next breakpoint. Continue. Right. There. Now it goes down to the next breakpoint. Refresh. So you can resume the program with continue. Right. Now I think that it might you might be able to go like C for next, right? All right, let's go ahead and go with next. You know what? There might be a problem with that end variable right there. I know I set it to 77, but I want to make absolutely sure that it was actually set to 77. Oops, not clear, but refresh. There we go. So what value does n have? I can say print n. Oh, there, it's 77. Right. This is visible, right? Yep, good. So you can look at this is why it's much better than a poor man's debugger, because you can go up to a point without having to put in a print statement. You can then print. You can view the value stored in a variable using print variable name, right? Whatever the variable name is. What about an array though? So what I'm going to do, I'm going to put that breakpoint back in for main and run it again. Yes. Refresh. Right. So what I'm doing here is obviously I'm just trying to print out the command line arguments that I received. But I want to know what's in there, right? Obviously I'm not printing them out correctly, because if I go next, you see that this garbage was printed out. So what's actually stored in there? Let's run this again. Yes. Refresh. Before we start printing them out, what's stored in there? So print. How many arguments are there? argc, 1. Oh, okay. Well, what is that argument going to be? It's going to be a.out. I know that already, but I want to make sure that I make absolutely sure. What happens when I try to print argv? Well, that's a character ***. Now we know what *** is, don't we? It's a two-dimensional array of characters. What's a two-dimensional array of characters? It's each row is a string, right? And so you've got an array of strings essentially here. But if I print that out, it's just printing a memory address. Right? Why? Well, because it's a memory address, right? char ***. So how do I get it to print an array of values? You can say print argv at the size. I know the size because I printed it out up here. Right? Argv at 1 will then print it in nicely formatted print. I need to dereference it because it's a pointer. argv at 1. So it's a dereference, the name of the array, an @ sign, and you have to tell the debugger how big it is. Right? And in this case, it's 1. Right? There. It prints it as a string, and it's printing it out the entire fully qualified path here. And of course, if I actually printed this out, it would just be a.out. If I go next, it actually doesn't print that out. Do you see why? %d, %s. How many placeholders do I have? 2. But I'm only printing one thing, and I'm printing the wrong thing. What should I be printing here? If I want to print all the command line arguments. I'm only ever printing the first one. So, we found our first bug. Let's quit. Let's fix it. Array. How do I fix this? Well, I put in I and instead of argv sub 0, argv sub I. Recompile it. Oops. GCC. Recompile it. Make sure that you're using that G flag. And then run gdb. Right? Layout next. And there is a way to launch it with the layout already showing. I forget how to do it off the top of my head, though. Run it. Or actually, let's break at main. Run. Right? Next. Next. Oh, neat. Now it's printed it out. Print. How many args do we have? Well, 1, so that's not that interesting. If I go next, then it's going to simply just jump out of this for loop. Right? How do I provide command line arguments in order to debug those command line arguments? Set args A, B, C, 1, 2, 3. Right? And run it again. Not rerun, but run. Refresh. Right? Print. Arg C. How many should I have now that I set them? A, B, C, 1, 2, 3, and a.out. So there should be 7. Excellent. What are they? Print dereference argv at, well, I know that there are 7 of them, not 27, at 7. There we go. There they are. A.out. A, B, C, 1, 2, 3. These are the memory addresses and the offsets here. But otherwise it will take care of formatting strings for you. It'll also format integer arrays for you. Right? So I'll go ahead and go next, next. Oh, now it's printing them out correctly. A, B, C. All right, well, I'm convinced that this works, so let's refresh it. And that other bug was occurring at line 25 now. Remember, we changed the code, so it looks like we changed the code. Anyway, it's at line 25 that something happens. So I will clear 15, or clear main, and I will add another breakpoint, break at line 19, and I will continue execution. Refresh. There we go. All right, n is 77. Okay, I don't know what that is for. Why? Because I didn't put in good documentation. That's a magic number for some reason. But anyway, go. Create an array to sum the first 7 primes. So we see the intention here, right? Is that how you do it, though? Int star primes is equal to 7. What am I doing there? I'm making the pointer point to memory address 7. Does that belong to me? Probably not. And that's why when we dereference it in the next one and try to set the first one, we're trying to write to memory location 7, which is going to give us the segmentation fault. The segmentation fault tells us that it's at line 26. You will never get that by just running it from the command line. If I ran this from the command line, oops, quit, yes, a.out, segmentation fault, it's not going to tell you anything. Right? It'll tell you A, B, C, D. Right? Poor man's debugging is terrible because you have to, type a bunch of stuff and it's fragile, but it also doesn't work. Undefined behavior is undefined behavior. If you corrupt memory on a certain line, it could run for 100 more lines until it finally dies. You will never find out that you corrupted memory up here because in some instances, because it's undefined behavior. Anything can happen. It can chug along for a little bit while longer before it completely dies and seg faults out. So you need to use a proper debugger in order to find stuff like that. Oh, you know what? We know what the issue is already, so how can we fix it? Not memory address 7. What should I be doing here? Call to malloc. And I want 7 primes, so how big should it be? 7 times 4? Is that right? No. 7 times? Size of? I didn't hear that. GCC. I didn't hear that intentionally. There we go. GDB. All right. Layout next. Run. Oh, actually, break at, I don't know, line 15. Run. All right, so that's not where I wanted it. I wanted to break at 25. So continue. All right. Refresh. Next. Oh, wait. N. Print N. 77. This will not manifest itself as a segmentation fault. Why? Yeah, I never go past it, right? 77 times 4, what was it, 4? That's more than enough to hold 7 integers, right? So, or, right? 7, actually I do go past. 7 times 4? Yeah, no, sorry. What is print size of n? Right? 4. So I do go past technically, but it never manifested itself as a segmentation fault yet, right? So you do have to be careful here. This will not show up, but Valgrind would catch this really easy. Right? Probably a static analysis tool would catch this. You don't do size of variables. This works. Why? Because it looks at it, well, size of n. Okay, n is an integer, and an integer is 4 bytes. That's why we're getting 4 out of this. Right. So let's quit out of this. If nothing else, the GDB lets you walk through and, okay, something's happening on this line. Stare at it, right? Stare at it for at least 10 seconds until something comes to mind. Oh, yeah, that's right, duh. I used an equal sign instead of 2 equal signs, right? You stare at it long enough, and it comes to you. As an old math professor of mine said, right? When I asked him, why do you use, or what did I ask him? Why do you use n-degree polynomials to solve degree n recurrence relations? And he said, you just sit there and you stare at it long enough and you come up with that idea. Somebody stared at it long enough 100, 200 years ago and came up with that idea after trying 50 different things, right? That's how it actually happens. So let's run it again, see if it works. Total is 77. Is that correct? Remember, what were we trying to do here? Add all these primes up. You can pull out your calculators or you can just add them up really quick. The actual number is 58. So we've got a bug here somewhere. At least it's not crashing anymore though, right? So there's something still wrong here. GCC and GDB and layout next. Run. Oh, actually break at main and run. All right, so I've debugged it up to this point, right? Where I'm pretty sure that everything works. If I set another breakpoint at 34 and then continue, there we go, refresh. Let me go ahead and print out primes to make sure that all this stuff above worked, right? So print primes at, how many of them are there? 7 was the intention. 2, 3, 5, 7, 11, 13, and 17. Okay, well that looks correct, right? If I just hit next, it's just gonna jump over that. This is a function call. If you want to jump to that function, you can either set a breakpoint for that function, or you can step into it. Next just goes to the next line. Step goes into the next step of the program. And what the difference here is, let's rerun it from the beginning and continue down to line 34. If I just hit refresh, if I just hit next right now, it's just going to go to the next line. But if I go step, that will step into the function. Remember that primes, 7. What about n? Do you remember what n was? 77. Okay. So I'll step into that. And now I'm in the sum function. I've jumped past these declarations because there's nothing to debug there. It's just a declaration. If I print I, okay, that's 0. Print total, okay, that's 0. But there is a bug there. That's not always going to be the case. That depends on the operating system. It depends on the compiler. So what should I do there in order to sum things up? I should initialize it to 0. So bug number 1, write that down, right? Note that down in your copybook. Okay, next. In fact, if you'd used Clang or GCC, remember it said uninitialized variable? That's the line it was referring to. Total, and then total plus 5. Well, total could have garbage, so garbage plus 5 is still garbage. Garbage plus 6 is still garbage. So make sure that you're running those static analysis tools first and catching as much as you can before you get into the debugger. Well, what's wrong with this? Print n. Oh, okay. Well, but also print array. Remember, we know that it was 7 of size 7, and if we just do that, then we get all this stuff. But if I start treating it like an array of size 77, at 77, see all that garbage right, afterwards? 0, 0, 0, and then this garbage, and et cetera, that if I just continue, it'll ultimately print total is 77 for some reason, right? Exited normally, though. So, what's the problem? Oops. There we go. I should have set this to just 7, and if I had actually used it, I probably got an error from GCC and Clang with all the warnings turned on that you don't actually ever use n, so why do you have it? That would have been another red flag for doing this. Now I'm passing in the correct value, right? And int s, there we go. What else was wrong with sum? We didn't initialize it. Anything else that you see that's obvious? If not, let's go ahead and GCC it again, GDB it again, and layout next. Break at sum because I know that the problem's in sum. Run, refresh. All right, so remember that we're adding 2, 3, 5, 7, etc. What I'm going to, that means that total is going to start going up. Well, I could go line by line and print it out every single time, or I could set a watch to it. Keep an eye on total. Right? Watch total. So next. Oh, hey. N7, there was the old value. It started at 0. Then I added 2. Okay. Next. And now I don't even need to type n. I could just hit enter. It goes up to 5. Why? 2 plus 3 is now 5. Next. What's the next prime? 5, so now it's 10. 17, next prime is going to be 11. Next prime is 13, so I should expect 42, or 41. That was a bug in my head, not in the program here. The next one is what? 17? Or where were we? 17? All right, so 58, at which point we should stop. Okay, it's 58. That's what the value I should be returning, right? Except, what happens? Yeah, there's no return value here. Right? And you can also, I forget how to do it off the top of my head, and I don't have it in my notes here, but you can print the return value of a function. And it's going to end up being some garbage, right? So next, and that's where we get a print value of 7. It's just reading some random memory location or something. Right? Refresh. Why? Because it was whatever value was returned was just some random value on the stack. Right? So quit out of this. We'll fix our last bug here that we need to actually return total. There we go. And I'm also going to show you one other thing here before we get done. Here's a long function. Oops. Yeah, GCC. Actually, let's look at the long function first. Where is it? So what's it going to do? Well, it's not going to do anything, but it's going to run up to 1 billion, and it's just going to set a value. But what's going to happen when I gets up to 20,000? It's going to divide by 0. So let's see that without a debugger. Floating exception, core dumped. All right? Kind of like a segmentation fault, except that it's a division by 0. So let's fire up our GDB. Now we saw that because I made it obvious. What if that's not so obvious? Layout. break at main, and run. Right? Next, next, refresh, next, there we go. Next, I want to step into that function, right? Refresh, next. Whoa, this is going to take quite a while to get to the actual error condition, right? I could go ahead and put a watch on I. There. Keep going. All right. I don't want to do that. I know that it happens sometime at 20,000. So what I can do is I can set a conditional breakpoint. I can break at line 52 if I is equal to 19,999. Well, actually, let's go lower, 97. Right? There. Now I can continue, and it'll go 20,000 times already for me, right? Or 19,900 and some times, right? Oh, continue without paging. There we go. Continue, right? There. Now we've stopped. If I print I, oh, you know what? All right, how do I clear watch? Clear I? All right. I forget. All right, break at, what was it called? Long function. Layout, next, run. There we go. Next, 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 next. I don't want to do this 20,000 times, so let's set a conditional breakpoint. Break at line 52 if I is equal to 19,998, right? And then continue. There. Can't believe it, you're taking that long, but it didn't take this long earlier. Maybe I want to kick. There we go, finally. Well, it is taking much longer than a regular program. Why? Because it's simulating the program, right? You have a program running a program rather than just running the program directly. Print I, and you see that it stopped short of that 20,000. So you can set conditional breakpoint. Any C condition that you can write, you can put as a conditional breakpoint. So lots of tools here that you can use, and I've only touched the tip of the iceberg with all this stuff. Refresh. Right. And then, of course, next, next, print I. Not there yet. Next, next, print I. Uh-oh, something bad is about to happen. Next. There we go. Arithmetic exception on line 52. Why? Oh, 20,000 minus 20,000. Oh, of course, that's 0, and I'm dividing by it. Duh, right? All right. So lots of things that you can do. Oh, by the way, if you're caught in an infinite loop, you can also do a halt with Control-C. So if it just keeps going, you can go just like Control-C, just like from the command line. It won't kill GDB. It'll just halt your program wherever it is. And then you can start walking around and see, why am I caught in this infinite loop? What else did I have? You can continue. You can set conditional breakpoints. I think I got them all. But of course, that's only the tip of the iceberg. Even in my office, I don't remember this stuff off the top of my head most of the time. So I've got a little cheat sheet. And I provided that for download in Canvas. Of course, that's just one cheat sheet of many. There are probably hundreds or thousands of commands that you can use. The required viewing for this module is another run through GDB. Actually, I don't know how, but it turned out to be my top most video. I think that there are like 70 or 80,000 views on it already. But I published it like 2 years ago, and if you Google for GDB tutorial, it's still the top hit on Google for it. Apparently, there were no good GDB tutorials out there, until that video came along, right? If you GDB tutorial. If you just search for video, there we go. Hey, there I am, top hit. Right. And I go through these basic commands with a different program, though. Right? Actually, it is a different program. Yeah, it's much more substantial. And this is 23 minutes long. So take a look at that for even more hints and tips for how to use GDB. Okay. Looks like there's a question. I don't know. You're asking about Hack 7 in the live Q&A, though. You're going to have to move that over to the regular forum there. All right. Otherwise, any questions on? Nope. Okay. No questions? Then have a good weekend. Remember that we do have the midterm next week. So review on Monday and midterm 1 week from today.